So in this video we want to look at the idea of the measure of centre if we have a discrete probability distribution. And so we're going to look specifically at two different measures of centre, that is the mean and the median. Now these should be concepts that you're familiar with from earlier statistical work in previous year levels. So the mean value is what we would commonly refer to as the average, add everything up, divide by the number of things. The median value is the middle. Okay, so the 50th percentile. When we're talking about probability distributions, we refer to the mean as being the expected value. Certainly when we talk about discrete probability distributions, that is what we would expect to happen if we were to do this probability experiment repeatedly. That would be the average thing that would occur. Okay, so let's think about our understanding of mean and median just through a frequency table. So forget probability distributions for a minute. Let's have a think about if we had this example here. So we've got a frequency table that shows the number of children in each household in a particular street and the frequency with which that occurs. Okay, so this data is telling us that there are 4 households in this street with no children, there are 4 households in the street with 1 child, there are 8 households in the street with 2 children, etc. How would you calculate the mean number of children per household? So remember, to find the mean, we would need to add up the total number of children per household and divide by the number of households. So thinking about how we would work out the total number of children from this table is there's 4 households with no children, so that's 0 children. There's 4 households with 1 child, so we would need to do 4 times 1 to find 4 children. Okay. There's 8 households with 2 children, so that's 8 times 2, that's 16 children. Okay. There are 6 households with 3 children, so that's 6 times 3, that's 18 children in those 3 households. Sorry, in those 6 households. There are 2 households with 4 children, so that's 8 children in those 2 households in total. And then 1 household with 5 children. So multiplying those together. So we would do the frequency multiplied by the data value, okay? And then to work out the number of households, we would add up the whole column. So we've got 8, 16, 22, 25 households. Okay. So we would add up the values, which would be doing 0 times 4, plus 1 times 4, plus 2 times 8, plus 3 times 6, plus 4 times 2, plus 5 times 1. And we would divide that by the sum of the frequencies, which is 4 plus 4 plus 8 plus 6 plus 2 plus 1. Okay, so we worked out that's turned out to be 25. If we add these up, what have we got? 4 plus 16 is 20, 38, 46, 51. So 51 out of 25. Sorry, let me just check that I've added that up right. 13. Yeah. Okay, so 51 over 25. Sorry, so it's just going to be very slightly more than half. 51 over 25, Control Enter, it is 2.04. Now, an expected value, just because it's a discrete random variable, it doesn't mean that the average has to be a whole number, okay? We would still talk about the average number of children per household as being 2.04. It doesn't mean that any household has 2.04 children. It means that on average, that's what the households have. So close to 2, okay? We often hear about, well, many years ago there was an ad which talked about, the average household has 2.4 children, I think it was, or 2.6 children. Or average family has 2.6 children. It doesn't mean that any family has 2.6 children. So please don't round off your average values or your expected values just because you've got discrete data. Okay, so that's a really important thing. I find students do that frequently. Okay, so then if we wanted to find the median number of children per household, so let's just get rid of all that so we can see our data a bit more clearly again. So the median number is the middle number. So if we were to be able to list out this data in a list in order from smallest to largest, the median would be the middle value. So if we think about starting to do that, just to think about what that list of data would look like, there are 4 households with 0 children. So as we were going down the street and writing on our clipboard, we would have had 0, 0, 0, 0 written 4 times. Okay. Then there are 4 households with 1 child, so we would have had 1, 1, 1, 1. Okay, now they wouldn't have been you know, the houses wouldn't have been organised in order, but we would have had a list of numbers that then later on we order it. Okay, there were 8 households with 2 children. 2, 2, 2, 2, 2, 2, 2, 2. There are further 6 households with 3 children. There were a further 2 households with 4 children, and there was 1 house with 5. So we should now have a list of 25 numbers. We worked out that total frequency earlier. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25. Okay, so the middle value, when we're working out what is the middle value, we add 1 and divide by 2. Okay, so it's going to be the 13th value. Okay, it's not the 12.5 value. If you've got an odd number of pieces of data, there will be a value that's in the middle. Okay, and we've just worked out that it's the 13th one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's the middle there. Okay, that's the middle. There's 12 after it and 12 before it, and that value there is the middle. Okay, so the median number of children is 2. Okay, and this will, the median won't always be a discrete value, because if we'd had 24 bits of data, let's say this bit's missing, then the median would have been 24 plus 1 over 2, which would be 12.5. So it would have been the 12.5 value. So it would be between the 12th and the 13th values, and so we would average the 12th and 13th values. Now in this case that would still give you 2, but let's say it was halfway between there, then the median could be 2.5. So again, it won't always be a whole number value. Alright, but we don't have to draw out the full list all the time. So you do still need to work out where is the middle. So you will still need the total frequency. Okay, so your median value is add 1 and divide by 2 is the 13th value. Okay, so then you can use your table to work out in which category will the 13th value sit. So there's the first 4 values are zeros. The next 4 values are 1s. So that's 8 values all up. So we're not up to the 13th value yet. Then if we add on the next category, we've got, that's now 16 values. So that means if it was 8 values up to here and then 16 values up to here, the 13th value has to be in this grouping, and so therefore it is a median of 2. Okay. Alright, so we're not working with frequency tables though, we're working with probability distributions. So if we gave you this exact same information about these households as a proportion rather than the number of households, okay, so if 4 out of 25 households have 0 children, that's a proportion of 0.16. 16% of the households have 0 children, sorry. Similarly, 4 out of 25, 0.16, 8 out of 25, 0.32, 6 out of 25, you can confirm it, it's 0.24, okay? So all we're doing now is we're writing each value as a proportion, and so what that now means is that these all add up to 1. So when we think about finding the mean or the expected value, as it would be in a probability distribution, and if we've defined a discrete random variable now, n is the number of children per household, we've got the possible values for n, 0 to 5 in this particular street, and the probabilities of each of those options, so we've got a probability distribution here. The expected value of n we would write as this, expected value of n, which is the same as the mean number of children per household. And up here when we found the mean, we did frequency times number of children per household, frequency times number of children per household, and added all of those up, and then we divided by the total frequency. Now in this instance, the total frequency is 1. So we actually don't need that step at all because we're just dividing by 1. We can ignore that. Okay, so it's essentially just we're going to be doing, and that's because we've already divided everything by 25. We divided the frequencies by 25. So we've just done the dividing by 25 at a different point when we do using a probability distribution. So, but we still need to do the number of children times the probability. So we did this times this and added them all up. We're going to do exactly the same thing in the probability distribution. So it's going to be 0 times 0.16 plus 1 times 0.16 plus 2 times 0.32 plus 3 times 0.24 plus 4 times 0.08 plus 5 times 0.04. Okay, and yes, we would then divide by the total frequency, which in this case is 1, so it's irrelevant. So if we work that out, obviously 0 times 0.16 is 0, plus that's 0.16, plus that's 0.64, plus 3 lots of 24 is 72, so 0.72. That is, sorry, it's not 0.72, is it? Yes, it is. 4 lots of 0.8, that's going to be 3.2. And 5 lots, sorry, it's not 0.8, it's 0.08, it's my mistake. So it should be 0.32. And 5 lots of 0.04 is 0.2. Alright, add those up. You can do the whole thing with your CAS if you want, but you do need to be able to, work with decimals and fractions reasonably well by hand as well in the tech free paper. Plus 0.32, so it's not bad, giving yourself some practice as you go. So, as we would expect, it shouldn't give us a different answer. It's exactly the same information given in a probability distribution. It's 2.04, which is what we found with the frequency table. So we simply need to do the data value multiplied by its probability and then add them all up to work out the expected value. For the median, okay, so again up here we worked out that the median was the 13th value, and so then we worked out gradually added the frequencies until we worked out in which category was the 13th value, and it was this one. Now when it's a probability distribution, the median will be the 50th percentile, so it will be where the probabilities add up to 0.5. Okay, so same idea, we need to gradually add up the probabilities, so they add up to 0.32, and then we add on they add up to 0.64, and so that means 0.5 is somewhere in this group. Okay, so you add up the probabilities until you exceed 0.5, and then that's the category where the median sits. If it added up to exactly 0.5, so let's say, what would we need that to be? Let's say that's 0.18, okay, and so then these add up to exactly 0.5, then the median is halfway between those two categories. So we would average those two categories, and we'd say the median is at 2.5. Okay, but in this case it wasn't, it was going to sit in there, and so the median is 2. So the median of n is 2. Okay, so let's work through an example. A spinner is divided into 4 sections labelled 1 to 4. The spinner is spun and the number where the pointer lands is recorded. If x represents this number, the following table gives the probability distribution for x. Okay, so we can spin 1, 2, 3 or 4, and those are the corresponding probabilities. We want to find the expected value for this spinner. So expected value of x, we take each data value and multiply it by its probability. So we're going to have 1 times 0.25 plus 2 times 0.2 plus 3 times 0.3 plus 4 times 0.25. Okay. Now, I'm writing it out so you can see exactly what's happening, but you would do those calculations in your head as you go. 1 times 0.25 is just 0.25, 2 times 0.2 is 0.4, 3 times 0.3 is 0.9, and 4 times 0.25 is 1. Okay. So 0.4 plus 0.9 is 1.3, plus 1 is 2.3, and then plus 0.25 is going to be 2.55. So the expected value for the spinner is 2.55. If we were to play this game lots and lots of times and average our score, it should turn out to be 2.55. Okay. Find the median for the spinner. Okay, so we gradually add up the probabilities until we get to the category where we equal 0.5 or we exceed 0.5. So 0.25 plus 0.2, so together they are 0.45, so we're not quite at 0.5. Adding that one on, we're now up to 0.75, and so therefore 0.5 sits somewhere in that category, and so the median value of x is 3. Okay, so the expected value of a probability distribution x is written as E of x, or we can use mu, the Greek letter mu. We tend to use mu a bit more when we're looking at continuous random variables for the mean, and E of x when we're looking at discrete, but they are interchangeable. It's found by summing the product of x and p of x. So we do each data value multiplied by its probability and sum those to work out the expected value of x. Note that the expected value for a discrete distribution does not need to be an integer. So don't round your expected value off, it's an average. Okay? The median of a probability distribution x is found by adding the probabilities from the smallest value of x upwards until either the total exceeds 0.5, in which case the value of x that has been reached is the median, or the total is exactly 0.5, in which case the median is the mean of the x value that has been reached and the next x value. Okay, let's do another example. A marble is randomly selected from a bag that contains 6 red marbles, 3 blue marbles, and 1 yellow marble. The game costs $3 to play. If a yellow marble is selected, you receive $8. If a blue marble is selected, you get your money back. If a red marble is selected, you receive nothing. Is this a good game to play? So we want to first of all let G be the amount of money that you gain in a game. Okay, so it's not profit, it's your gain. Okay, so remember it costs $3 to play. If we get a yellow, we get $8. So that's a gain of $5. Okay, if we get a blue, we get our money back. So that's a gain of $0. And if we get a red, we get nothing. So that's actually a loss of $3. So there are 3 possible values for G. Okay, probability that the gain is equal to that possible value. Alright, so we could lose our $3, okay, or you get our money back, which is a gain of 0, or we could win $8, but we've paid $3, so that's a gain of 5. So those are the 3 possibilities. Alright, let's work out what happens. We get nothing if we get a red marble. So this is the red marble. We get our money back, so we gain $0 if we get a blue marble. And we win our $5 if there is a yellow marble. So if we work out those probabilities, the bag has 6 red, 3 blue and 1 yellow. So we've got a total of 10 marbles there. So probability that we get a 6 is 6 out of 10 or 0.6. Probability that we get a blue is 3 out of 10 or 0.3. And probability of a yellow is 1 out of 10 or 0.1. Okay, I'm sorry, I have answered part B here in part A. So G was about simply listing out my possible values for G. Part A was about listing out possible values for G. So G could either be -3, 0 or 5. Okay, part C, in the long run, how much would you expect to win or lose per game? Okay, so this is the definition of an expected value. In the long run, this is what we would expect to happen. On average, this is what should happen. Now, if you only play the game twice, you know, you could lose both times, lose $3 both times and lose $6. Okay, but if you play the game 2,000 times, you should be, on average, earning the expected value. Okay, so we're looking for the expected gain. Okay, which is going to be -3 times 0.6. We're working out the expected value of this probability distribution, plus 0 times 0.3 plus 5 times 0.1. Okay, so -3 times 0.6 is -1.8, plus 0 times 0.3 is 0, plus 5 times 0.1 is 0.5. So that's -1.3. Okay, so therefore, on average, or in the long run, we would expect to lose $1.30 per game. Now, it's completely impossible to lose $1.30 in any given game, but if you were to play this game lots and lots of times, on average, you should be coming out behind by $1.30 each game. Okay, so therefore, it's not a good game to play. So you want an expected value of 0 or positive, in this case, in order for this to be a good game for you to play. Otherwise, on average, you're going to lose. Casinos set it up so the expected value for every game is a negative value. It's positive from their point of view. It's negative from your point of view. Okay, now I want to work through a sort of extended example to establish some patterns of what happens when we're working with expected value. And these patterns will apply when we're working with expected value of a discrete distribution and also of a continuous distribution, which we'll look at further down the track. So it's going to take us a little time here to establish these patterns, but once these are established, these are patterns that hold for all probability distributions. Okay, so sometimes we may wish to find the expected value of a function of x. Okay, so we might have the expected value of f of x. So let's think about some different functions of x. I know that sounds sort of contrived, but some situations where this might be happening. So if we have a spinner with regions numbered 1 to 4, In the game, the spinner is spun and the player earns the points equivalent to the number showing on the spinner. The probability distribution for x, the number of points won per spin, is given below. Okay, so we want to calculate the expected value of x. Now we're going to be doing a lot of calculation here, so I'm going to do this fairly quickly. So we're doing 1 times 0.2, which is 0.2, plus 2 times 0.3, which is 0.6, plus 3 times 0.4, which is 1.2, plus 4 times 0.1, which is 0.4. And we're adding that up. 0.2 plus 0.6 is 0.8, plus 1.2 is 2, so it's 2.4. So we have an expected value of 2.4. Obviously, when we spin the spinner, we can't ever earn points of 2.4, but if we were to play this game hundreds of times and average our score, it should, in the long run, average out to be 2.4. Okay, so now let's think about trialling different versions of this game. So in version A, the player gets the value of the spinner plus 3 points. So if they spin up a 2, they get 5 points. Okay, if they spin up a 4, they get 7 points. So what's shown on the spinner plus 3 points. Okay, so if A is the number of points earned per spin in version A of the game, then A is essentially our x values plus 3. So it's the same probability distribution, except we're going to have added 3 onto all of those x values. So now we have 4, 5, 6, and 7. Okay, so we want to work out the expected value of A, the expected winnings in this game, which is the same as the expected value of x plus 3. Okay, so expected value of A, which is actually the expected value of x plus 3, it's going to be, and again we're going to do this a bit, so I'm going to do it quickly if I can. 4 times 0.2 is 0.8, 5 times 0.3 is 1.5, 6 times 0.4 is 2.4, 7 times 0.1 is 0.7. 0.8 plus 1.5 is 2.3, 4.7, 5.4. Now, interestingly, if we compare that to our expected value of x, we see that this is 3 more. Okay, so actually, the expected value of x plus 3 is just the same as the expected value of x plus 3. Okay. Now that makes sense. All we did was add 3 onto all the points values. If the average here was at 2.4, then the average here should be at 5.4. Okay. Let's think about version B. The player gets double the value of the spinner. Okay, so if you spin the spinner and you spin up a 3, then you get 6 points. Okay, so if B is the number of points earned per spin in version B of this game, then the probability distribution for B is shown below. So B is equal to 2 times x. So instead of it being 1, 2, 3, and 4, it's now 2, 4, 6, and 8, the points that you earn. So we're going to calculate the expected value of B, which is the expected value of 2x. Okay, and again it's going to be 2 times 0.2, which is 0.4, 4 times 0.3, which is 1.2, 6 times 0.4, which is 2.4, and 8 times 0.1, which is 0.8. And so that is 1.6, 4, and 4.8. So again, thinking about compared to our original expected value, we have actually doubled our expected value. So this is just 2 times the expected value of x. So the expected value of 2x ended up being 2 times the expected value of x. Okay. So do you think we could infer from that that if it was expected value of 3x, we tripled our points? We just need to do 3 times the expected value of x? Yes. Okay, let's combine those together. So in version C, the player gets double the value of the spinner plus 3 points. So if they spin up a 1, they get 2 times 1, which is 2, plus 3, they get 5 points. Okay, so double and add 3. If they spin up a 2, they get 2 times 2, which is 4, plus 3, 7 points. If they spin up a 3, 2 times 3 is 6, plus 3 is 9 points. And again, if they spin up a 4, 2 times 4 is 8, plus 3 is 11 points. So we now have, these are the possible points that could be won in version C of the game. We're going to work out the expected number of points in version C of the game. So the expected value of C, which is the same as the expected value of 2x plus 3. Okay, so again, 5 times 0.2 is 1, 7 times 0.3 is 2.1, 9 times 0.4 is 3.6, and 11 times 0.1 is 1.1. So adding those up, we have 3.1, 6.7, 7.8. Okay, Okay, so we might speculate. Let's think about what was expected value of x, remember, is 2.4. So if we were to do 2.4 times 2 and add 3, we get 7.8. So this is actually just 2 times the expected value of x plus 3. Okay, let's have a look at one more version. In version D, the player gets the square of the value of the spinner. So if they spin up a 2, you square it, they get 4. If they spin up a 4, you square it, they get 16 points. Okay? So here's our new probability, here's our new probability distribution here. Same probabilities, but different point values. We want to work out the expected score when we play version D, so expected value of D, which is, sorry, that should be an x there, which is equivalent to the expected value of x squared. Okay, so again, we're doing 1 times 0.2 plus 4 times 0.3, so that's 0.2 plus 1.2 plus 9 times 0.4 is 3.6 plus 16 times 0.1 is 1.6. Alright, and adding those up, that is 1.4, 5, 6.6. Okay, so our question is again, what was expected value of x? Was 2.4. So if we do 2.4 squared, we get 5.76. We don't get 6.6. So this one does not equal the expected value of x squared. Okay, so where it was sort of quite easy in these previous examples, it's not as easy here. So in summary, this is what we found. We found that the expected value of x plus 3 was the same as the expected value of x plus 3. We found that when we were doing the expected value of 2x, it was the same as 2 times the expected value of x. We found when we did the expected value of 2x plus 3, it was the same as 2 times the expected value of x plus 3. However, when we tried to find the expected value of x squared, it wasn't the same as the expected value of x all squared. Okay, so when we are finding the expected value of a linear function, that is directly related to expected value of x. So if we have the expected value of ax plus b, that is just going to be a times the expected value of x plus b. But if we have the expected value of some other function of x, it is not just that function of the expected value of x. Okay, so it's only when it is a linear relationship that we can sort of expand out the expected value of x, if you like. Alright, so in summary, this is what we have here. The expected value of ax plus b is the same as a times the expected value of x plus b, but if we have a non-linear function, then we have to set up a new distribution and work it out, which is exactly what we did up here. We squared all our x values and worked out our expected value of x squared. Now, expected value of x squared is something we will be working out frequently because it's part of another calculation we need in the next lesson, and we'll be doing that quite often. So it is something that we need to do. And also, if we're working out the expected value of some other function of x, we would set up a new probability distribution and do that value times each probability and sum them all together to work out the expected value. Okay, example 3. For the random variable x, defined as follows, find expected value of x. Okay, so it's going to be 0 times 0.64, which is 0, plus 1 times 0.288, which is 0.288, plus 3 times 0.432, which is 1.296, plus, sorry, it shouldn't have been 3 times that, it should have been 2 times that. So that's 0.864, I can do that one in my head. And 3 times 0.216 is going to be 0.6, 3/16 of 48. So 0.648. So again, as I said, try and build up the practice of working with decimals in your head. I know for some of you that's not something you're that comfortable with, but that's all the more reason to do the working in your head as you're practicing to familiarise yourself with those techniques. Okay, so adding these up, 0.288 plus 0.864, whoops, plus 0.648. There's nothing to say if you've got your CAS, absolutely you can just type into the CAS from the outset, 0 times 0.064, 1 times plus 1 times 0.288 plus 2 times 0.432 plus 3 times 0.216 and get to your answer straight away. Okay, our expected value of x, apologies, is 1.8. Okay, so if we want to then work out the expected value of 3x plus 1, okay, we could change all our values, 3 times x plus 1, this will become a 1, this becomes a 4, 3 times 2 is 6 plus 1 is 7, 3 times 3 is 9 plus 1 is 10, and do it again. But what we've just established is when this is a linear function in here, this is the same as 3 times the expected value of x plus 1. So having worked out our expected value of x, that is 3 times 1.8 plus 1, so 6.4. Alright, if we have the expected value of 5 minus x, now again, this is a linear relationship here, okay? So this is just going to be the same as 5 minus the expected value of x. So that's just going to be 5 minus 1.8, which is going to be 3.2. Now, expected value of x squared, however, we actually need to work out our new probability distribution. So we need to square each of those values, okay? So they're going to become 0, 1, 4, and 9. And this time we're going to be doing 0 times 0.064 plus 1 times 0.288 plus 4 times 0.432 plus 9 times 0.216. So we've squared each of the x values, okay, and multiplied them by their respective probabilities. Okay, so this is going to be 0, this is still 0.288, 4 times 0.432 is 1.728, plus 9 times 0.216 is 1.944. Alright, so if we add that plus 0.288, it is 3.96, the expected value of x squared, which is not the same as the expected value of x all squared, which would give us 3.24. Alright, example 4, I think this is the last one for this video. A car insurance company estimates the probability that a customer will make 1 claim in a year to be 0.07, the probability of 2 claims in a year to be 0.01, and the probability of 3 or more claims in a year to be essentially 0. It's so unlikely it's not worth taking into the calculations. If x is the number of claims made per year per customer, then the following probability distribution can be set up. Okay, so x is the number of claims made per year, lowercase x can be 0, 1, 2, or essentially that's irrelevant, so we're really just dealing with this, okay, because that's a probability of 0 from there onwards. Find the value of k, and so therefore we need the total probabilities to add up to 1, and so k is going to be 1 minus 0.07 plus 0.01, so that's 1 minus 0.08, and so it is 0.92. So 92% of the time a customer will make no claims in a year. Okay. Calculate the expected number of claims made per customer per year. So expected value of x, which is the number of claims per customer per year, is going to be 0 times 0.92 plus 1 times 0.07 plus 2 times 0.01. And again, this is essentially, we can essentially ignore that. Okay, so what have we got? 0 plus 0.07 plus 0.02, so 0.09. So the expected number of claims per customer per year is 0.09. Now we don't round that off. We're not suggesting that any one customer makes 0.09 claims. We're saying that's an average value per customer. So we could then work out, well, that would mean that per 100 customers, on average, they would make 9 claims a year. Okay, per 1,000 customers, on average, they would make 90 claims per year. Okay, so the car insurance company charges customers $800 a year for insurance and estimates that the average claim costs the company $1,000. If G represents the yearly gain made by the insurance company per customer, express G in terms of X. Okay, so the gain made per customer, they obviously gain the $800 from them that they pay, but then if they make a claim, they're going to be taking away $1,000 times the number of claims, and remember X was the number of claims per customer per year. So this is the connection between the gain made by the insurance company and the number of claims made per person. Okay, so obviously even if a person makes 1 claim, technically the insurance company actually loses money on that person for that year. But given that this is the average number of claims made per person per year, this is still working out for them. Okay, So calculate the expected yearly gain per customer. So we want the expected gain, which is actually the expected value of 800 minus 1000x. And so because that's a linear relationship, we can essentially expand that out. It is 800 minus 1000 times the expected value of x, which is 800 minus 1000 times 0.09, okay, which is 800 minus $90. So they still make $710 per customer per year on average. Okay, so yes, that might fluctuate per individual customer, but over, the scheme of their thousands and thousands of customers, on average, they can budget for making profit of $710 per customer. So these are the sorts of, this is a very simplified example, but these are the sorts of calculations, risk and expected gain, expected loss, and expected number of, accidents, etc., that are happening in the ideas of risk management and insurance. Okay, so the work today is from exercise 13D, practicing expected value and median measures of centre for a discrete probability distribution.